Good afternoon, and welcome back to a video on Intermediate Algebra MAT 1033. This is video number 4. We're going to be doing a review of fraction arithmetic. So the first question to answer is, what is a fraction? And before we answer that question, let's remember the last videos where we talked about what is a reciprocal. So a reciprocal of a number is the number you want to multiply by it to get 1. Right? So we think of the reciprocal of 2 as 1/2, 3 as 1/3, and now we're going to extend that notion through multiplication to get this whole class of objects called fractions. But it begins quite that simply. A lot of times we start fractions as being like pieces of a pie or other ways of visualizing it, but really to get at what fractions do and why their arithmetic looks like it does, you can start with just what is a reciprocal. And so all you have to know about reciprocals is how they behave with these numbers that they multiply by. A number times its reciprocal is 1. And this is the kind of fundamental cancellation that we're going to get when we define what a fraction is. So let's do that. A fraction is going to be a pair of numbers, a combination of two numbers, a top number called the numerator and a bottom number called the denominator. And really, by combination, I don't mean something particularly special here. I mean multiplication. A fraction, which you write as a number over another, a over b, is just the top number times the reciprocal of the bottom number. So specifically, a over b is just a times 1 over b, where 1 over b is the reciprocal of b, the number that you would multiply by b to get 1. And this is actually a nicer way to look at fractions than trying to think of them as carving up pieces of a pie or any of that kind of nonsense. At least as long as what we're really trying to do here is not cut up pies, but get some product or some arithmetic or some kind of algebra problem figured out. And what we're going to look at is that all of the rules that we're about to address are going to basically stem from just this idea, just the idea that it's a numerator times the reciprocal of the denominator. And what is a reciprocal? It's a number that you multiplied by a number to get 1. That's all you need. That's fractions just flow from those two facts. And of course, some of maybe the other properties of algebra, like the distributive property and that kind of thing. So to begin with, the easiest kind of arithmetic you can do with fractions is to multiply them. The rule for that is you just take the top number times the top number and the bottom number times the bottom number. Again, these rules, I'm going to write them down in their general form and give some examples, but they're not going to come, their proof is not going to come from anything else other than the definition that we've used, even though I'm going to skip the proofs for this class. If you're interested in why these things are what they are, please, by all means, let me know and I will make an expanded video for that. But here's just a numerical example. What if you wanted to take 3/2 times 4/7? Well, you could multiply 3 by 4 and multiply 2 by 7, and it would be 12/14. And even though this isn't reduced, I know some of you are probably freaking out because, that's not reduced. You could reduce the 2 and the 4 first. Yes, you can. But this is a perfectly valid fraction. This is 12 times the reciprocal of 14. And it's going to be numerically no different than what you would get if you reduced. So in light of that, it's sometimes easier to just think about it in its unreduced form. Now let's talk about reducing fractions. There is always more than one way to write any fraction, and this is because a times its reciprocal, or a over a, is just 1, and 1 times anything is just itself again. So for example, let's go back to 12/14. You could factor out a 2, or if you notice the common 2 on the top and bottom beforehand, you could have canceled in the beginning. But even if you didn't, how does 12/14 simplify? Well, you could factor out the 2 from the top and bottom, and then 2 divided by 2 is just itself, or 2 times its reciprocal is just 1. And so you just get 6/7. So the takeaway from this is that if you can factor the top and bottom, then we can cancel what they have in common. So it's a nice thing to try to do to get the top and bottom to be factored and then cancel whatever you see repeating. What about unreducing fractions? Is that a thing we can do? Yes, and in fact, that's going to be a really important thing to know how to do. What we're going to do is we're going to take advantage of a trick where we just multiply by 1, but it's going to be a kind of weird looking version of 1. So for example, if I want to unreduce 3 halves, I can do it. Let's say I want to multiply it by 4 on the top and bottom. So 4 over 4 is just 1, so equality is going to hold all around here. And then by the definition of fraction multiplication, you times the top and the bottoms together, and you get 12/8. And so 12/8, by this chain of equalities, is really no different from 3 halves. So fractions have a lot of different guises, a lot of different forms. The same fraction value, 3 halves, is the same as the fraction value 12/8. There's no difference between those two things. They just have different forms. Now, dividing fractions is actually something that we've already done. And that's because of the way that we defined division. The way that we defined division is by multiplying by the reciprocal. And that's still going to be our definition. But now we have to know, what's the reciprocal of a fraction? What number do you have to multiply the fraction by in order to get 1? And then we'll know all about division. And it's not too terribly hard to see that if you want to take the reciprocal of a fraction a over b, it's just the flip of that fraction. It's b over a, right? This is your keep, change, flip rule. Because if I multiply those two numbers together, a over b and b over a, well, you get 1. You get a times b on the top, you get b times a on the bottom. Those are, of course, the same thing, and like over like gives me 1. So now that we found the reciprocal of a over b, we could say what it would be to divide by a over b. We would just be multiplying by its reciprocal. So for example, if I take a over b and I want to divide it by c over d, then I just take c over d and I flip it. I take its reciprocal and I multiply by that. And this gives us a times d over b times c. Here's an example worked out of that. So here's 3 halves divided by 4/5. That's 3 halves times 5/4. Top to top, bottom to bottom, that's just 15 over 8, baby. Hey dog, we heard you like fractions, so we put fractions in your fractions so you could divide while you divide. Oh no, what are we going to do about this? It's just division. It's just division. This is not a problem. This is not going to be an issue at all. Let's just rewrite this as division. So what is a divided by b divided by c, right? So let's rewrite that middle division part as a division symbol. And now we're just dividing by a fraction, which we just learned how to do. We multiply by that fraction's reciprocal. So a over b over c is the same as a times c over b. And now how do we deal with that? Well, you probably already know, but let's just talk about this one last bit of whole number logic here. Every whole number is also a fraction. It's just a fraction in disguise. It's a fraction over 1. If I want to look at it that way, I could look at a as a times 1 over 1. This is because a is equal to 1 times 1, and 1 is its own reciprocal. So again, I'm just multiplying by 1 on the top and bottom here, no big deal. That's just a over 1. You could also, and you may also know, that a divided by 1 is just itself again. So we can always write whole numbers, or any number we please, as a fraction over 1. And so our last little bit of work to do here is that a times c over b is really just a over 1 times c over b, but that's just a times c over b. b times 1 is just b. But let's actually take this further. I want to remark that there's a few different ways that we could write a times c over b, and they're all the same. You can always choose to divide into one or the other of those terms. This is either a over b times c or a times c over b. Why are we allowed to do that? Think about this for a moment before we go on to the next thing, and think about how you might explain, is this legit? And why is it legit? Well, here's one way that we could see why this is legit. A times c over b, by the definition of what we said fractions are, is just a times c times b's reciprocal. And now that we've written things as all multiplication times a reciprocal taking care of our division, Multiplication can be done in any order. I can switch around the 1 over b and the c. I could group together the a and the 1 over b. It's all totally fine. Associativity and commutativity bias the rest of this. So there's actually no preference between either of these forms. You can write them however you want, however is most convenient. You can cancel if possible. All right, now let's talk about the tricky thing to do with fractions. Whenever you see a fraction and you are adding or subtracting that beast, you need to pause and you need to think to yourself, do I have like bases or not? Because this is actually the hardest thing to do with fractions. And maybe that's not so surprising. We designed fractions to work with multiplication and division. That's how they are defined, is through multiplication and division. So maybe addition and subtraction, it shouldn't be too surprising that they are a little trickier. Let's consider the like bases case first, the case where we have the same denominator. 1/5 plus 2/5 is 3/5, right? If I have like bases, I just add the numerators. Why? I mean, you could hear it linguistically. If I have one of these things called fifths plus two of these things called fifths, I get three of these things called fifths. No duh. But come on now, like in this form, is it so clear that that's what we have? Yes, I know you're familiar with pieces of pie. Cut the pie up into 5 pieces. One of them plus 2 of them is 3 of them. Yes, yes, yes. But why algebraically is this the case? Can you think of a reason? If you answered the distributive property, you're correct. Because check it out. 1 over 5 plus 2 over 5, that's just 1 times 1 over 5 plus 2 times 1 over 5. We know how multiplication and addition play together. If I'm multiplying by a common term, I can factor it out. That's the distributive property in reverse. Then I just have 1 plus 2 times this thing called 1 over 5. That's 3, of course, times 1 over 5, which by the definition of a fraction is 3/5. And in general, we would say that if we add like bases, we just add the numerators. And if we subtract like bases, we just minus the numerators. Whether or not that gives us a positive or a negative number, you need to be quite careful, but that is how we do it. What about unlike bases? You can't do it. You cannot add unlike bases. You have to make those bases the same. How? Well, the unreducing trick that we learned. For example, if I wanted to add 5/3 plus 1/2, I need to get those bases to be the same. But what if I multiplied by these suspicious-looking versions of 1? This is, of course, this denominator over itself, and this denominator over itself. Well, if I carry out that multiplication top to top and bottom to bottom again, I wind up with 10/6 plus 3/6. Now that I am in terms of sixths, I can just add the numerators together and get 13/6. Notice that the new denominator is neither of these two denominators up here. We wind up with a completely different species of fraction on occasion when we add or subtract fractions. This is par for the course. This is something to be aware of and to be ready for. But the trick was to get those bases to be the same. Once we had like bases, the addition was pretty easy. You just keep the denominator and add the numerators if addition's what we're doing. And so we could do this trick in general. Take one base, multiply it top and bottom. Take the other base, multiply it top and bottom, and then add them. Now, there's a lot of talk here about least common multiples and reducing and all that. And we could talk about that in a little, but for right now, this is the pattern I want you to learn, that we can always do this. And this always works, whether it's the simplest case is, something we might have to decide. But this is a surefire way to add two fractions or subtract two fractions that have unlike bases. So now let's start with the critical notes. There's going to be some properties here. I want you to copy these. Pause the screen right now and copy these examples and these rules. Let's continue on. There's a couple more to do. Copy the remainder of these properties and these rules. These are how you deal with fractions. So now I want you to try some praxis exercises. Practice this for yourself. Try to do these, and you use the properties that we have above in order to do so. Pause the video at this time and see how you do. Okay, let's see how things went. So, number 1, We rewrite this as division. Division is multiplication by the reciprocal, and top to top, bottom to bottom, we get 15 over 2. Number 2, in order to multiply fractions, it's top to top, bottom to bottom again. And we could reduce this fraction if we wanted to by factoring out a 3 from the top and bottom and canceling it if we see commonality on the top and bottom. Now, some of you probably know that we could actually do our cancellation right here. As soon as we see a common factor on the top and bottom, we could take care of it right away. So if I were to see that 3 goes into 9 and into itself, I could divide by 3 on the top and bottom here and cancel right away. Then I just have 7 times 3 up top, which is 21, and 1 times 10 on the bottom, which is 10. Either way, you should have gotten 21 over 10. So here's another one. Let's take a look at 8 plus 2/5. This is 8 over 1 plus 2 over 5. If I times 1 over here, I just get 2. If I times 5 over here, I get 40. And 1 times 5 is just 5. So this is 42 over 5. Here's another one where we have unlike bases. If I multiply the 3 over here, I get 15. If I multiply the 6 over here, I get 1, and 15 minus 6 is 9, and so we wind up with 9/18. That does reduce. We could take 9 out of the top and the bottom to get 1/2. Now, some of you who are familiar with the least common multiple angle of things here are probably like, well, you really could just manipulate this until it's a 6, and that's true. Let's take a look at that. So if I notice that I could make this base into this one easily, or with a smaller number than just their product, I could do that, but we're going to get the same number in the end. And we're not necessarily guaranteed that we don't have to simplify. For example, this would be 2 over 2 times 1/3, that's 2/6. Once it's in sixths, I take the difference between 5 and 2, and I get 3. But I still have to reduce. We didn't dodge reducing. We still have to think, well, 3 goes into the top and the bottom, so this reduces to 1/2, and we still get the same answer. We did have the luxury, of course, of working with smaller numbers than 9/18. That's true. But if you want a way that always works, the formula above for fraction addition and subtraction will always work. All right, that's been an overview of fraction arithmetic. Thank you for your patience, and good luck with your studies.